And recording should be started. Yes. All right. So we want to talk about fractured gradients, and that's part of basically your project as well, right? Why is it part of your project? Because remember we talked about these graphs, right? You have basically your equivalent mud density, which is your pore pressure gradient, right? Coming from the sonic log. Please use sonic log, not the resistivity one in your project. I think that resistivity is not correct. Use the sonic log that I gave you for calculating the pore pressure. And that's basically what you get from that sonic log, right? It gives you an equivalent mud density as a function of depth, right? After using the Ben-Eaton's equation, right? So this red line is coming from your sonic log, right? And then this black one is basically 0.5 pound per gallon, the trip margin, right? That's for the safety purposes, right? So once you calculate your equivalent mud density, you add 0.5 to each data point along basically the way, right? Let's see if I can write here. Why can I not write? I should be able to write. Okay, not this one, but I want to write for sure. Let's see why it doesn't let me write here on the screen. Maybe I should go to draw. Okay, why draw is not active? Tablet mode, maybe. Nope, I can still write here. Sorry guys, let me fix this issue. Yeah, this is protected view, so that's why. Okay. All right, sorry. Okay, so here it is. So this is the 0.5 pound per gallon for each data point. So you add 0.5, you get basically the trip margin, right? So any data points that you have, you add 0.5 to that data point. From the sonic log, you get your trip margin line, right? Okay, now in order to basically have your mod program, you also need the fracture gradient, right? Why do you need fracture gradient? Because you don't want to frac your reservoir or any formation as you drill through, right? So you don't want to frac the formation. So in order to do that, you would need to find a way to find the fracture gradient, and that's the topic of this basically presentation. But once you have found your fracture gradient, which is basically this blue line, again, through the Ben-Eaton's equation, then you can basically find this kick margin, which is 0.5 per pound per gallon again, but this time to the left side for the safety purposes. And once you draw this kick margin line, then you can design your drilling fluid program by, why is it changing slide for itself? Sorry, this is a new computer, so that's why I'm still getting familiar with it. So anyway, once you get this, then you can start from the very bottom, right? At your trip margin and go straight up vertically until you hit the kick margin line. This is the mud density for that portion of your drilling fluid, Sam. That's the question you asked, right? What is your drilling fluid density? This is that drilling fluid density. You go up, you read the value. This is your drilling fluid density. Okay, for this portion from here to here, right? Once you hit the kick margin, you go horizontally. You don't want to use the same drilling fluid density for this top section here. The reason is if you use this density, you will frac the formation. So you have to reduce your drilling fluid density. That's why you go horizontally until you hit again the trip margin. You go up again until you hit the kick margin line, and so on and so forth. It gives you the density for each portion of the wellbore that you are drilling. Also, it gives you the set depths of your production, intermediate, and surface casing depths. Any questions here? Any questions? No? Is it clear, Sam?
So is it like the mud density is from the bottom, like zero? Like, I mean, from the bottom until like he hit that kick margin?
Yeah. Yeah. So from these steps to these steps, this will be your mud density, and this is the set depths of your production. Of course, it's the end of your wellbore, right? And this basically gives you the set depths of your intermediate casing here at the top. So it gives you two things. One, it gives you the mud density that you need to drill for that portion of the wellbore. It also gives you the set depths of your casing. Make sense? Another example here on this slide. The same basically example. You see now the numbers here, right? So for example, here from probably around 11,000, maybe 800 feet to all the way to 15,000 feet, which is the bottom of your wellbore, you have to use a mud density of 17 pounds per gallon. And this is the set depths of intermediate casing. So 17 pounds per gallon for this portion. Right? Now, what does it mean that when I'm saying for this portion, what does it mean? How can you drill up to some point and then suddenly change the density? How does it work? I mean, you start from the surface, right? You have a wellbore, of course, right? And what does it mean that drill this portion up to here from this point to this point with a 17 pound per gallon? Well, once you design your system, you have set all these other casings, right? You have set basically your conductor, your surface, your intermediate casing, right? And you can start injecting 17 pounds per gallon from the surface all the way to the bottom, and nothing will happen because you already set your conductor, surface, and intermediate casing. So any formation above these depths will not be touched by your drilling fluid. That's why we put the casings, right? So it means that once you set your intermediate casing, the new mud density that you need to use to continue your drilling is 17 pounds per gallon. That's what it means. Up to these depths that you reach, right? And for this one, it's around 13.9 maybe pound per gallon. So once you set your surface casing at this depths, right, then you want to continue your drilling up to 11,800. You use 13.9 pound per gallon mud. And then from the surface, probably you have a conductor, of course. Conductors is different story, but let's assume that the next casing that you have here, this is intermediate, of course. This is surface casing. So your surface casing use a mud density of probably around 9.5 pounds per gallon. Does it make sense? Any questions here? Nope. All right. If you got it, that's awesome. So the topic of this lecture is basically, well, how do we calculate the fracture gradient? Let's do a quick example on the formation pressure. So you have a, this is basically the topic of previous slides. You have a well depth 14,000 feet, formation pore pressure expressed is equivalent mud density of 9.2 pound per gallon. And overburden is 1 psi per feet. What is the pore pressure at 14,000 feet? Well, the equivalent mud density of your formation pressure is given to you, and pressure is equal to 0.052 density depth, right? And the pressure equivalent density is basically given to you, 9.2 pound per gallon. So pressure is 0.052, 9 pound per gallon, 14,000 feet. That's it. That's pore pressure. Because equivalent mud weight formation pressure expressed in equivalent mud weight is 9.2 pound per gallon given to you. So that's first part. Pore pressure at, well, what's the difference between these two? These two are the same, right? Yeah. Probably this one was pore pressure gradient because it's in PSI per feet. So in order to find the gradient, it's very easy, right? Gradient means pressure over depth. That's 0.052 multiplied by depth. So that is 0.05, sorry, multiplied by density, multiplied by 9 pound per gallon. That gives you pressure over depth, which is PSI per feet. So this one is done, this one is done. Matrix stress. So matrix stress is basically overburden stress, which basically is calculated through this equation. This is overburden stress, this is pore pressure, this is matrix stress. This is also called effective stress, right? Just keep in mind always that if you have a formation and there are pores here, there are two forces acting on these pores. One force is coming from the weight of the rock on the top, weight of rock, and other force is basically coming from the fluid inside these pores acting basically to the wall. So these two forces are opposing, so there is a effective stress, which is called sigma V, and that is equal to overburden minus pore pressure. From the top, from the fluid, effective stress, okay? Now, this question asks you to calculate the effective stress. It has some applications which we did not use, but of course you can do these calculations. Now, this equation, you can divide all the sides by depths, right? They become gradients, right? This is overburden stress gradient. This is pore pressure gradient. This is effective stress gradient. This one is given to you 1 psi per feet. And what else? Yeah, the pore pressure you calculated from the previous step. You can calculate the effective stress gradient here, right? And you can calculate also the matrix stress, not just the gradient, by multiplying this number by 14,000 feet, right? That is done in this slide. All right, any questions? Nope. All right, so this was kind of a review. You guys probably knew this thing, and fracture gradient is done through several equations we have here, and we will discuss it. And again, the reason is that we don't want a fracture over formation. It can be computed from well logs, equations, things like that, correlations, or it can be done through experiments, which is called the leak-off test. And you can guess how leak-off test is being done, probably. You take a rock, you inject a fluid into the rock at high pressure, you increase the pressure until your rock fractures, right? And that's where is the fracture resistance of your rock, right? Pretty simple experiment, but that's called leak-off test. If you heard that test name, that means this test, okay? It's very practical in hydraulic fracturing to do the leak-off test because they want to see at what point your formation will fracture. I need to connect my charger, just a second. Meanwhile, if you guys have any question, I can respond. All right. All right. Anyway, so you guys don't have any question apparently. So that's what we do, right? So multiple equations can be used, right, for fracture gradient. We will go over a couple of them here. One is called Hubbard-Willis, and in Hubbard-Willis, basically, what it does is basically it gives us two gradients. F is basically fracture gradient here in this equation, and it gives us two gradients. One gradient is basically the minimum and one the maximum. So it doesn't give you an exact value for your fracture gradient. It gives you a range, right? What would be probably the minimum fracture gradient or maximum fracture gradient at some specific depths. Pretty simple equation. It's just a function of your pore pressure gradient. That's all. Okay. So we'll do an example on that. That's it. As simple as that. Next one is called Matthews-Kelly, and it's basically based on a constant that we will discuss it. It's called matrix stress coefficient Ki. Sigma, remember we just calculate the effective stress, that's the same sigma, and this is pore pressure gradient. Okay, so this case coming from some specific graphs that we will talk about it. We'll do an example on that, but overall, this is basically, again, a simple equation, but it gives you a fracture gradient for any depths, right? And finally, we have the Bennetton's method. And Bennetton's method for fracture gradient is a function of overburden stress, which is this one, a pore pressure gradient, a constant, which is one of the rock properties is called Poisson's ratio. Poisson's ratio is a property of the rock that is dependent on its strength, how hard your rock is, and can be determined experimentally, or if you know the type of the rock, you can find its Poisson ratio, or they are determined based on the location. So we'll talk about that as well. And then this is pore pressure gradient. So these are the three methods, okay? Let's do an example so you guys get familiar how to solve the problems and also do your project. So here is the problem. A Texas Gulf Coast well has a pore pressure gradients of 0.735 psi per feet, depth 11,000 feet. Calculate the fracture gradient units of pound per gallon using each of the above three methods that we just discussed. Summarize the results in a tabulated table, right? Okay, so first method, Hubert-Willis. It's basically the minimum and the maximum, right? So the minimum is calculated using this equation, 1/3, 1 plus 2 pressure over pore pressure over depth. And pore pressure over depth is basically the pore pressure gradient is basically 0.735 psi per feet. And you put into the equation, very simple, very, very simple. It's basically 0.823 psi per feet. Make sense? All right. So that's the minimum. Sorry, let me close this application here. All right. So, and maximum, right? So that was the minimum. You calculate the minimum. You put the numbers. That then you can convert it into pound per gallon. Pore pressure gradient can be converted into pound per gallon by simply dividing the pore pressure by gradient by 0.052. Okay, does it make sense? So that's it, right? And okay. So next one is basically the maximum pore pressure gradient from that equation. So half 1 plus pressure over pore pressure gradient. You put the equation, very simple. You get the numbers and done. That's it. Okay. So this is 16.68. The minimum was 15.83. Okay. So what it tells you is that you're probably, if you use a density of 16.68, a mud density more than 16.68 pound per gallon, you will fracture this formation. Any questions? All right. So that's it, right? And the Matthew and Kelly method basically uses sigma over D, right? The effective stress, and also a K that we need to determine, right? So P over D, we have it here, 0.735, that's done. We need to find the sigma, right? Sigma, again, you can use this equation. S is basically pressure plus sigma. Sigma is overburden stress minus pressure at any specific depths, right? Overburden stress is given to you to be 1 psi per feet. Pore pressure is given to you. So sigma is simply 0.265 psi per feet multiplied by 11,000 feet, which is the depth at which these basically calculations are being done, and 2,915 psi, right? So this is again straightforward calculations. And now, in order to calculate K, you would need to do something else. What you would need to do is to calculate a normal. So do you guys remember that we talked about a graph? If you have basically some of these parameters changing with depths, let's say one of these porosity indicators, right? This is the normal trend, right? This is the abnormal. So we talked about a method that basically uses the effective stress at similar depths, right? What we said that we assume that if you have the same porosity parameter, it could be sonic log, whatever rock, right? And this is depth. It could be sonic, it could be resistivity, it could be DC, whatever parameter you use on the x-axis. If you have the same porosity value indicator, which can be determined by this vertical line, then the the effective stress at these 2 points should be equal to each other, right? So what we do here in these calculations is to find these depths. We are at this point, we want to find these depths, right? And this depth is at normal pressure gradient area, right? So we already found this 2,915. So sigma at this point is 2,915 psi, right? Now, based on this assumption, sigma at this sigma normal should also be 2,915 psi, right? So once you do that, then overburden doesn't change. At this point, it's 1 psi per feet. But the only thing that changes here is your normal pressure gradient, which is 0.465 in that area. So this is normal pore pressure gradient. And then sigma we assume to be the same, so 2,915. So you can calculate the depth. So this is 5,449. This was 11,000 feet. Any questions here? This might be confusing. So you guys, I expect you guys have some questions here. No question. So you guys all got it? All right, awesome. So if you guys got it, so once we calculate these steps, we go to some plots, which is here. It's a bit slow here. We go to these plots, and these plots are basically that depths that you calculated as a function of matrix coefficients for Matthew and Kelly's method, Ki. Okay, since this well is in South Texas area, each area might have a different trend. You can use that depth, 5,000 something, go to this curve, go down, read the value of Ki. So based on these calculations, Ki is 0.685. And we can now use the equation here. We put all the inputs. We have K, we have sigma over D, we have P over D, 17.63 pound per gallon, or 0.9165 psi per feet. So this method is a bit more complex, but still we can do it, right? Another picture here, that's the same picture there, just with more clarity, 5,685 K. All right, last method, Benetton method. The only thing that we don't know here is what is gamma, or Poisson ratio again, Poisson ratio. And also, you might assume that you have 1 psi per feet, but sometimes we do have also graphs for different areas. For example, this graph, I'm not sure why this is slow. Overburden stress by Eaton's, right? You can use this plot as well, depending on depths. It gives you kind of different values for your overburden stress at different depths, okay? So for example, at 11,000 feet, if you go here, your overburden stress is 0.96. At the other depths, it might be different, right? So at any depths, you would be able to calculate its own overburden stress gradient, right? So once you do that, you can also find the Poisson ratio from the graphs again, okay? So for example, this is a Gulf Coast Poisson ratio and West Texas Poisson ratio graphs, right? And for example, at 11,000 feet, you go there, you read the value of Poisson ratio. In this case, is 0.46, right? So this is coming from the graphs, right? There might be correlations for your Poisson ratio because that's a rock property, but graphs are always easy if we have them, right? So then we have everything we put into the equation. This found from the graph, Poisson ratio from the graph, 0.9267 and 17.82. Now, if you compare different methods, you see that this is the minimum, this is the maximum Hubert-Willis, right? And Matthew and Kelly and Ben Eaton methods, pretty similar results for your fracture gradient, right? Now in your project, you would need to do this for all the depths that you have, right, given to you. So make sure you digitize your graph again using the plot digitizer, find all these properties that you have. Also make sure for your overburden stress, you use this graph. This is also in your book, I believe. You can take it from slides, digitize this graph as well. And this gives you overburden stress as a function of depth. You can, if you want to use Ben Eaton's method, you would need to have the Poisson ratio, which you can again use this graph to find your Poisson ratio as a function of the depth. So that concludes basically this. Now you will have, if you would do it correctly, pore pressure calculations, trip merging, fracture gradients from either of those three methods, and kick merging, and you're ready to find your mod program using this method and casing set depths. And next step is casing design, which you already know how to do it. So any questions?
So I have a question. Like, I put the log, the sonic log, on the website, but I kind of
Yeah.
like kind of confused with about, like, that x1 and there's x2 and y. So the y should be like, okay, I think the y here.
Um,
It's y2 and there's y1.
See, for example, I have this graph, right?
Okay.
Let's see if I can save this picture. Yeah. Let me save this picture. Okay. Let me share my whole screen. I'm not sure if I shared the whole screen with you guys. All right. So I'm going to go here and search for this is a new computer. I'm not sure why it is that slow. Webplot digitizer. All right, so we go there. You launch the app. And you load your image. You can use this option from the right. So load, choose file. And then mine is in the pictures. Select that one, open. And here it is. So it asks you to, it automatically asks you to basically 2D plots, right? This is X and Y plot. That's what you want to do for your graph as well. You want to align axes and you want to proceed. So one thing you do is select X1, which is basically I selected here at 0 and 0. Make sure you do it very accurately. This is my X2. This is my Y1 exactly at the same point. And this is my y2. Now look at what points did I select. For my x1 is 0, right? x2 is 0.6, right? My y1 is 20. My y2 is 0, right? Then you hit complete on the right side and you put those numbers in, right? Your x started from 0 to 0.6. So that's 0. I don't change that one. This should be 0.6. And then that one is 20, right? And then my y2 is 0. And then you hit OK. All right, done. So now you want to digitize this line. You select points on this line. Let's say you want to digitize this line, right? Now make sure you put your points are exactly on the line. You can select as much as you want, as close as you want, right? And once you're done with selection of your points, you can, on the left side, there is an option view data. You see there? You hit that one, and these are all data points that you selected from 0.29 and 1.23 all the way to whatever that is. And then you can also download it as CSV file, or you can just select all and copy, whatever you want to do with it. You have your data points. Does it make sense? Did it make it clear? All right, so any other questions, guys?
Will you post this the link to this website?
Yes, I can put it in the chat maybe now.
Yeah. Thank you.
That works for you guys. Let me see. I mean, I'm not sure if this link will work, but try it. No.
So we can digitize as many as
Data points as you
data point.
Yeah.
But we have an option like to not like be specific, you know.
What's that?
Like, do we have it like an option? Like, do we have to be like really specific on that, the point data, or do we?
Yeah, you want to capture all those changes, right? Make sure when you select your data points, select as many as you can, because it will cover the whole curve for you. Make sense? And then for each point that you select digitize there, you would need to calculate a pore pressure and a pressure gradient, and also a kick margin and a trip margin. And then you can plot it, and then you can design your mod, basically program. All right. No more questions? All right, so I'm going to stop recording, and